So before we start this one, let's talk about the geometric series again for just a second. When you have a geometric series, we know that we're going to find A and R. And we can find a partial sum because that formula is A times 1 minus R to the n over 1 minus R. And then the sum of the entire series is A over 1 minus R if the absolute value of R is less than 1. So you need to make those notes. Those are important to use and know. You can find a partial sum for any R, but we can only find the sum of the entire series if the absolute value of R is less than or equal to 1. So pause the video, write those down. They're important. This next one is interesting. It says write the number 2.317 repeating as a ratio of integers. So you know that's 2.3171717 ... So we start off with, think about the fact that let's start with 2.3. And then we're going to add 0.017 plus 0.00. Let's see, 3 decimal places, and then a 17, and so forth. Well, let's do one more. So we're taking out these 5s. We have 1, 2, 3, 4, 5, 1, 7, plus ... So this means that we have 2.3, and this is 17 over 1,000, which is 10 to the third. And then we have 17 over 10 to the fifth, and 17 over 10 to the seventh, and so forth. Now you can see from here to here, we multiply by 1 over 10 squared, which is 1 over 100. And from here to here, we multiply by 1 over 10 squared, which is 1 over 100. So that's going to imply that my R is 1 over 100 or 1 over 10 squared. But the problem is we start multiplying after this term. So the geometric sequence really starts here. So if we start with A is 17 over 10 to the third, and our R is that, then if we want to find the sum of the series, we would add the 2.3 at the beginning. So what we really have is it says to write it as a ratio of integers. So we're going to say 2.3 plus A over 1 minus R. So we have 2.3 plus A is 17 over 10 to the third, which is 1,000, over 1 minus R, which is 100. So we have 2.3 plus 17 over 1,000 divided by 1 minus 100 is 99 over 100. So we have 2.3. Well, let's go ahead. It says a ratio of integers. So let's take that 2.3 out. Let's write it as 23 over 10. 2 3/10 plus 17 over 1,000 times 100 over 99. So that gives me 23 over 10 plus 17 over 990. So when we add, we can add and reduce to be 1147 over 495. So your repeating decimals, we find that 2.317 repeating equals that ratio. Repeating decimals are fractions. That's why they fall into rational numbers. They can be written as fractions. So let's look at another one. It says, show that the sum from n equals 1 to infinity of 1 over n times n plus 1 is convergent, and find its sum. So let's say convergent and sum. Now if it's divergent, you can't find the sum. So keep that in mind. let's start with the first few terms. A sub 1 is 1 over 1 times 2, which is 1/2. A sub 2 is 1 over 2 times 3, which is 1 over 6. A sub 3 is 1 over 3 times 4, which is 1/12. A sub 4 is 1 over 4 times 5, which is 1/20. Now, this is not geometric because we're not multiplying by a common ratio each time. So we're going to go back to here, and this says that our series, that if the partial sum is convergent and the limit approaches a value and exists, then the series is convergent. So that's where we're going to head with this. We're going to use this concept. So we're going to look at a partial sum and look for convergence there. So let's go back to this problem. I'm going to start it again. So we have the summation of from n equals 1 to infinity, 1 over n times n plus 1. And we know it's not geometric, so let's look at a different method. Let's look at the partial sum. So we're going to say S sub n is the sum from I equals 1 to infinity, and we have 1 over I times I plus 1. Now this kind of looks like partial fractions, and good news, let's go there. So we're going to say 1 over I times I plus 1 equals A over I plus B over I plus 1. Kind of needed a different variable. So we're going to multiply by the common denominators. So we end up with 1 equals A times I plus 1 plus B times I. So 1 equals AI plus A plus BI. So 1 equals I times A plus B plus A. So then A plus B equals 0, and A equals 1, so B equals -1. That means we can come back up to our summation and say that this is the sum from I equals 1 to infinity. And we have, we're going to plug them into here where A is 1 and B is -1. So we have 1 over I plus a -1, which makes -1 over I plus 1. So now let's look at that summation. So if we put in 1, we have 1 over 1 minus 1 over 2. And if we put in 2, we have 1 over 2 minus 1 over 3. If we put in 3, we have 1 over 3 minus 1 over 4. Plus ... plus the final term would be 1 over n minus 1 over n plus 1. Now, do you see a pattern here? Look at the fact that these two cancel and these two cancel. So the front of the parentheses cancels with the one before it. So that means this would cancel with the next one, and this would cancel with the previous one. So it ends up being 1 minus 1 over n plus 1. Now, here's the interesting fact. This is called a telescoping sum. Think about a telescope like in pirate movies, or telescoping the spyglass, how they collapse it in. That's why it's called a telescoping sum, because it collapses and the pieces in the middle cancel out. So now let's go back to this formula here. We know it converges to a value, so we can find the summation, and it says the limit exists. So let's try that. So we say the limit as n approaches infinity of S sub n equals the limit as n approaches infinity of 1 minus 1 over n plus 1. So when we plug that in, we get 1 minus 1 over infinity, which goes to 0. So the limit is 1. So since we have a limit, let's go back. When you look at this stuff, we looked at the partial sum here. We got it to be convergent. And then the limit exists at a real number. So the series is convergent. And the sum equals S. And S is the sum of the series. So let's come back to here. This tells me that the sum from n equals 1 to infinity of 1 over n times n plus 1 equals 1. So it's convergent, and the sum is 1. The next one says, show that the harmonic series. The harmonic series is the famous series. Kind of like the Fibonacci sequence is the famous sequence. So it says the sum from n equals 1 to infinity of 1 over n. So we have 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over n. So that's our harmonic series. And we're supposed to show that it's divergent. It definitely is divergent. It looks like it's getting smaller, but it is divergent. Show that it's divergent. This is not geometric, so there is no common ratio. So there's no pattern to look at. So we're going to look at partial sums again. So let's find S sub 2. That means we add these two. If we add these two, we get 1 plus 1 half, which is 3 halves. If we add S sub 4, that means we're adding 1 plus 1 half plus 1/3 plus 1/4. So, by the way, this method is not one you're asked to do much. The technique was, if you look at your book, the technique was accredited to a French scholar, Nicole Orisme, and he lived in the 1300s. But what he did here is he took this S sub 4 and he compared it to, we say it's greater than 1 plus 1 half plus 1/4 plus 1/4. Notice that 1/3 is bigger than, this 1/3 right here is bigger than 1/4, so that is a true statement because this is a greater than. So since we have a greater than, it's true. And then over here, this equals 1 half plus 1 half plus 1 is a total of 2. We write it as 1 plus 2 over 2. So think about S sub 8. It equals 1 plus 1 half plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. We're going to do a similar technique. Here we have those two, and then we can take and put eighths in here. So we're going to say this is greater than 1 plus 1 half plus 1/4 plus 1/4 plus 1/8 plus 1/8 plus 1/8 plus 1/8. Now this part over here is equal to 1 plus 1 half plus 1 half plus 1 half. So you see all the halves happening? So this is technically equal to 1 plus 3 halves. Now we're looking for patterns because sequences and series are about patterns. And S sub 16, I don't know that I have space for this, equals 1 plus 1 half. And I'm going to quit telling it to you and just write. and this is greater than 1 plus, we're going to keep the 1/2, and then we're going to do 1/4 plus 1/4 plus 1/8 plus 1/8 plus 1/8 plus 1/8. Can you guess what goes next? Yep, 1/16 plus 1/16, all of these places. So this equals 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2. So this is 1 plus 4/2. Now notice if I'm at S sub 2, I have 3/2. We call it 1 plus 1/2. Let's do away with that 3/2. S sub 2 is equal to 1 plus 1/2. Remember, we're looking at patterns. S sub 4 is greater than 1 plus 2/2. S sub 8 is greater than 1 plus 3/2. S sub 16 is greater than 1 plus 4/2. So we can say that S sub 2 to the n, notice we're only looking at powers of 2, is not equal to, it's greater than 1 plus n over 2. This shows that as our sum gets bigger, so the limit as n approaches infinity of S sub 2 to the n equals the limit as n approaches infinity of 1 plus n over 2, which is infinity. So the sequence S sub n is divergent. Therefore, the harmonic series is divergent. We have a theorem. Theorems are important. We could prove them. It says if the series, the sum from n equals 1 to infinity of an is convergent, then the limit as n approaches infinity of a sub n equals 0. Now, it's not the other way around. So, note, the limit as n approaches infinity of a sub n equals 0 does not imply convergence. So just keep that in mind. It does not imply convergence. We have another theorem. It's not necessarily a theorem. It's the test for divergence. And the test for divergence says if the limit as n approaches infinity of a sub n does not exist, or if the limit as n approaches infinity of a sub n does not equal 0, then the series, the summation from n equals 1 to infinity of a sub n is divergent. So if you take the limit and it does not equal 0, or if you get does not exist, then the series is divergent. Now your question is, what about the one back there? The one we did back here, we got 1, but this was a partial sum. So it's different when you have, this theorem says if n is approaching infinity. So if n is approaching infinity and your limit does not exist, or if your limit does not equal 0, then we have divergent for the series. So let's look at one of those. It says the sum from n equals 1 to infinity of n squared over 5n squared plus 4. So what we want to do is we want to look at this series. It says test it for divergent. Is it divergent or convergent? So let's look at the limit as n approaches infinity of n squared over 5n squared plus 4. So if we take the limit, the easiest way to do it is to divide by the highest power of n in the denominator. So we divide by n squared and we get 1 over 5 plus 4 over n squared. This approaches 0, so we get 1/5. So since it's a value, we can say the limit as n approaches infinity of a sub n does not equal 0. So by the test for divergence, the sequence that we have from 1 to infinity of n squared over 5n squared plus 4 is divergent. Just a note real quick, if we find the limit does not equal 0, then we know it diverges. If we find the limit equals 0, it tells us nothing. So if the limit of the infinite series approaches 0, we know nothing. If the limit of the infinite series does not approach 0, we have divergence. So that's important. One more thing, your summation laws have not changed since we looked at them, and they're similar to your limit laws. So if you have series, you can always pull a constant out, like here. If you have the summation and you're adding two series, you can add them separately or subtract them separately. Those things kind of make sense. The last note I want to show you is that a finite number of terms doesn't affect it, the convergence or divergence. So for example, if you were going to look at this sequence here, we can find the sum of the first few, and we know that it's convergent. So when we find that the finite sum is convergent, we find that the infinite sum is also convergent. There's one more problem I wanted to do with you. It says the sum from n equals 0 to infinity of x to the n, where the absolute value of x is less than 1. It's kind of interesting because you're looking at a very small x value. So let's start with, notice that this is n equals 0. So that means that we have, if we were to write this out, we have x to the 0 plus x to the first plus x to the second plus ... So that means that we have 1 plus x squared plus x to the third. Now notice the absolute value of x is less than 1. So this means we're multiplying by x each time. So we're multiplying by x. So this means our ratio is x, and it is defined to be where the absolute value of x, which is r, is less than 1. So we have a geometric series, and a is 1. So that means we can find the sum. So the sum is a over 1 minus r. So a is 1 over 1 minus x. So then we can say that the summation from n equals 1 to infinity, from n equals 0 to infinity of x to the n equals 1 over 1 minus x, where the absolute value of x is less than 1. So this is a fun section. I hope you have a good time with it. Well, as good of a time as you have. Have a great day. Thanks.